Welcome back. Now we'll look at paper 13 from the May-June 2024 series, and this is actually the final paper one in that series. Right, now, as always, the mark scheme for this paper has been released, so I will recommend checking that out as well. Just looking at their additional answers. And of course, if the video is too slow, then watching at 1.25 or 1.5 times the speed is also recommended. Right, the first one, complete the following description. A kibibyte has a something prefix. Right, so here when it's saying prefix, and to me this is a bit strange because, usually prefix, that means the start of a word. But I guess here they're actually talking about the base. Like here I guess they're saying binary. And I mean the reason they call it a prefix is because, here we're saying, it's going to be base 2, right? The prefix is 2. And I guess the power is, in this case, going to be 10. Right, so 3 kibibytes is the same as something bytes. So if you think, 1 kibibyte is going to be 1024, right, then 1024 times 3, that should just be 3072. Because also this was also in paper 12. So I think, that one I remember. Right, the next one, a megabyte has a something prefix. Right, so if it's mega, that's going to be 10 to the power of 6. So here we're going to say denary. I think decimal would probably be okay, but maybe denary is better. Right, then 2 terabytes is the same as something gigabytes. So if we think, 1 terabyte is going to be 1000 gigabytes. Right, therefore, of course, 2 terabytes, 2000 gigabytes. Right. Then we want to convert this denary number to hexadecimal. So there's a few ways people do it. I mean, some people like to convert from denary into binary and then from binary into hexadecimal. But if we just want to do it directly, we just want to write down the positional value. So if we go 16 to the power of 1, right, that's going to be 1. Okay, then if we go 16 to the power of 1, right, that's going to be 16. And then if we keep going, this one we actually don't need. But 16 to the power of 2 is 256. So of course, 256 is too big, right? We can just ignore that. So we want to think, how many times can we divide 241 by 16? And I think this is actually going to be 15 times because, 10 times will be 160. And therefore, 5 times 16 is going to be 80. Right, so if we just think, 160 plus 80, right, that's going to get us to 240. So here, this is going to be F, okay, because, 15 in hexadecimal is F. Right, and then, that means we're just going to have 1 remaining, okay, because, again, this F is going to be 240. Of course, the 1 is going to be the 1. Right, then we want to state what is meant by an overflow in binary addition. So here, this is where we add 2 numbers, but the resulting sum is too big to store in the given number of bits. So let's just say that, adding numbers, or maybe adding 2 numbers. I guess we can say 2 or more numbers. Right, and let's say, and the resulting sum. Right, is too big. I suppose not too big because it can also be too negative. Let's say maybe requires too many bits, or maybe let's say requires more bits than are available. Available. And something to note with overflow is that overflow can only occur if we're adding 2 numbers with the same sign. Because, let's say we're using 8 bits, and imagine we're using signed. Okay, so we should hopefully know that the range for 8-bit signed binary is going to be, 2 to the n minus 1, right, but then we just want to minus that. So if we do that calculation, and again we're saying 8 bits, right, so 8 is going to be n, right, that gives us a, let's say, negative value of minus 128, right, that's the smallest value. And then the biggest value, that's going to be, 2 to the n minus 1, and then we go minus 1 like that. So that's going to give us, positive 127. So let's just think, for example, if we add 2 numbers of the same sign, let's go, 127 plus 1. Of course, this can cause overflow. Likewise, if we go, let's say, minus 128 minus 1, so again, minus and minus, plus and plus. Both of these can cause overflow. But if we add numbers with a different sign, so let's say for example 127, right, plus, and well, let's say plus -1, right, well, this is never going to cause overflow, because if we think, you know, this is always going to go towards 0. Likewise, if we've got a negative number, right, plus, let's say 1, right, plus a positive number, again, that's also going to go towards 0. So yeah, that's another key factor about overflow, right? You can say it's only going to occur, right, if you're adding numbers with the same sign, right? It's not going to occur if they've got different signs. Right, then computers use character sets when representing characters in binary. Complete the table by identifying the number of bits each of the character sets allocates to each character. Alright, so yeah, this one hopefully is not too difficult. You just need to remember. So ASCII, well, that's going to use 7 bits, so that's going to give us 128 different characters. Extended ASCII, I mean, basically this is going to include, well, of course, all of the regular, like sort of, yeah, Latin, numbers, right, punctuation. But this also includes, for example, characters with accents, like an A like this. I don't know, maybe there's another one, something like that. But anyway, right, that's going to use 8 characters, get 8 bits, which will give us 256 different characters. And then, right, Unicode, well, that can be, right, from 8 to 32. So, for example, something like UTF-8, right, so UTF-8 just means, well, sort of Unicode using 8 bits. I think maybe it's like Unicode transformation format or something like that. But what we say is, well, we say the common characters, again, for example, well, the letters, the numbers, sort of basic punctuation, right, that's only going to use 8 bits. Some of the other languages, maybe, for example, like Russian or something, might use 16 bits. Other languages, I don't know, like Chinese, Japanese, possibly Arabic, right, that might use 24. And then, for example, some of the emojis, well, they'll use 32. Okay, so here we would say, let's say sort of the more common characters are going to use less. And then, yeah, let's say sort of some of the emojis right there are obviously going to use more. Right, then we want to explain how the word clock is represented by a character set. Right, so I think here then we want to say that each character is going to have a unique binary code. And I think often for this, I mean, it's kind of stating the obvious, but they just want to say, well, it's going to be represented in sequence. So of course we have the binary for this bit, sort of, yeah, capital C, but then obviously the binary for this lowercase l. So yeah, let's just write that. Let's say, right, each character, right, yeah, each character is given a unique binary code. And you know, for example, if you just say binary code, like, they probably won't give you the mark. Yeah, I think unique they often put in bold. Right, so a unique binary code. Yeah, I don't know, and then we can say which are displayed in sequence to kind of represent the whole string. I guess, well, not displayed, maybe stored. Okay, yeah, which are stored in sequence. Right, to represent the whole string. Alright, and yeah, hopefully that should be enough for 2 marks. Right, then a photograph is stored as a bitmap image. The photograph has a resolution of 4,000 pixels by 3,000 pixels high. Right, the bit depth is 4 bytes, okay, or well, 32 bits. Calculate an estimate for the file size of the photograph in megabytes. Right, I mean, so the image, the image file size calculation is quite easy, right? Even if you forget it, well, just think logically. Of course, you know, one thing you need to know is, well, how many pixels are there? And then when you know how many pixels there are, well, then you want to say, like, what's the size of each pixel? So effectively, of course, by just multiplying all of this together. Right, so I guess if we do, what, 4,000 times 3,000, right, that's going to get us, what, 12, and then, well, here we've got 3 zeros, here we've got 3 zeros, so that should give us, what, 12 million. Right, then I'm going to go, well, 12 million, and to be honest, you know, my maths is not very good now, but yeah, I think most people here have probably got better maths than me. Right, that's going to be, what, 48 million. Right, and then of course, well, this is going to be in bytes. Right, therefore, if we want to go from bytes to megabytes, well, mega, remember, is going to be, what, 10 to the power of 6. So yeah, if we then just go, what, 48, I mean, I'm just going to write it like this, so 48 times 10 to the 6, right, then divided by 10 to the 6, well, that's just going to equal 48 because, of course, well, they're going to cancel out. Right, the photograph is compressed before being uploaded to a web server. Give 3 benefits of the photograph being compressed using lossy compression, right, instead of lossless compression. So I guess the obvious one, well, the file size will be smaller. Yeah, right, so file size smaller than lossless compression. And you know, honestly, like if you just say file size smaller, I mean, probably they'll give you the mark. But yeah, sometimes they do actually want you to specifically say, you know, than lossless compression. So I'm just going to say, right, loss compression. Right, well, yeah, let's go lossless. Right, the next one, I mean, if they're saying, well, uploaded to a web server, then we can also say that, yeah, I mean, I guess we can expand this number one, right, file size smaller than lossless compression, right, hence uses less space on the web server. Because yeah, sometimes they do just want this kind of extra, let's say extra explanation that's kind of relevant to the specific scenario. Right, so I think the next one, of course, well, because the file size is smaller, then it's going to mean that the transfer or the upload is going to be faster. So yeah, upload to web server, right, will be faster. Right, because, yeah, well, yeah, so because file size is smaller. And obviously, well, this, yeah, obviously write file size in the exam. Right, and then I suppose the next thing you can talk about, well, it's going to use less bandwidth. And this could also be important, like maybe if you're limited in terms of bandwidth, you know, you could be on a mobile network and you have like a monthly limit, for example. So, all right, well, let's go upload. Okay, right, so upload uses less bandwidth. Right, let's say, yeah, hence, I don't know, maybe like won't cost as much, or yeah, won't exceed the monthly limit. Yeah, let's say, right, won't exceed monthly limit, for example, on a mobile network. Yeah, so I think hopefully they should accept all of those. Right, then we want to explain how run length encoding RLA will compress the photograph. Now I think this one, you know, most people remember, but I will explain it because, well, yeah, some people might have forgotten this. So let's say we have an image and, I don't know, maybe we have, for example, like white. Yeah, so we have like 5 white pixels, right, then, I don't know, maybe a blue pixel, then a red pixel. So instead of, you know, writing, and of course, well, white, that's going to be what, 255, 255, 255. Because, well, we've got, yeah, 255 red, 255 green, 255 blue. Now, you know, instead of just writing like, well, obviously, yeah, 255 for this one, right, 255 for this one, you know, of course, yeah, for, well, all, you know, all of these. What we can instead write is, well, if we just go 5, and then basically we have 5, and then, you know, obviously these 255s. So what that's saying is saying, well, you know, we've just got 5 repeated whites. Then, of course, we're going to have blue. And if we think, well, let's say 1, right? So we've got 1 blue. And that's going to be, what, 0, 0, and then 255. And, of course, well, red, well, that's going to be 1, yeah, 255, then 0, 0. So let's try and explain that. Let's say maybe consecutive pixels of the same color. Right, yeah, consecutive pixels of the same color. Let's say, yeah, can be represented. Right, let's say, yeah, as a count of those pixels. Right, let's say, yeah, and their color value. Let's say maybe like hence maybe reducing duplicate, yeah, let's say hence reducing duplicate colors, I guess. Yeah, hence reducing, or let's say duplicate pixel values. Yeah, and making the photo smaller. Yeah, so I mean, hopefully that's enough for 2. Now, these questions, you know, you could give an example like this. So to say, well, if we have 5 whites, of course, yeah, represent that as 5, and then, yeah, 255, 255, 255. Right, we want to identify 2 elements of a bitmap image that can be changed to reduce its size. So, I mean, this one, if we just said, well, it's going to be the number of pixels. Now, the number of pixels, well, that's going to be the image resolution. Of course, the resolution is what the, let's say, the number of rows by the number of columns. Right, and then, I mean, the next one, well, of course, just the bit depth or the color depth. I mean, let's call it maybe bit depth. I mean, yeah, what do they call it here? Yeah, here they call it bit depth. So, you know, actually bit depth, color depth, it just means the same thing. Yeah, and I mean, like, we could put in brackets, so we could just go, well, number of pixels, although I think we don't really need to do this. Alright, number of pixels in image. Yeah, that's just a sort of simple definition. And of course, well, this is the number of, let's say, the number of bits per pixel. Because, you know, honestly, like, when it says identify, usually that just means give the name. You know, we don't really have to explain them. Right, the following table shows part of the instruction set for a process. The process has 2 registers, the accumulator and index register. Right, so yeah, here's just a list of instructions they give us. And, you know, I think in the exam, maybe it's good just to have sort of 30 seconds just reading those. Right, so the current contents of memory shown below. The current contents of the accumulator and index register are also shown below. Complete the table by writing the contents of the ACC after each program has run. Right, so LDM50, well, that's going to be load using immediate addressing. And, right, immediate addressing, well, that just means, yeah, load in this value. So here then, well, that's just the, yeah, the denary value 50. Right, then we increment the accumulator, so that's going to go to 51. Right, then we just subtract, and again, this is using immediate addressing. So we just subtract 1. So, well, that's just going to go to 50. And in effect, you know, if this is a real process, or, well, I guess if this is a real, let's say, compiler, so I mean, if you've written this, let's say, in a high-level language, right, or, you know, if you've written it in assembly, then of course, well, the assembler is just going to probably remove those, because I mean, basically, it's going to realize they're redundant, right? They're just cancelling each other out. Right, then we have LDI 51. So I think that's going to be load using indirect, and of course, here we can just check. Yes, so indirect addressing, the address to be used is at the given address, load the contents of this second address into to the ACC. And I mean, I've said this in the other videos, but if we think indirect addressing, well, that's where we have the double brackets. So for example, the fetch to code execute cycle, where we say, well, load the contents in the address, right, you know, kind of in the MAR, and yeah, load that into the MDR. Yeah, that probably wasn't a good explanation. I mean, so what this is saying, well, kind of, you know, get the address that's stored in the MAR, and, you know, then go to this address, and yeah, that's where the instruction will be stored, you know, and of course that instruction we copy into the MDR. Right, so what that's saying then is what we want to go to, yeah, so we want to go to 51. Right, so we go to 51, well, it tells us 50, so then we want to go to this, yeah, memory address 50, and that's going to be the data 48. Right, and then what we want to do, we want to add 52, and notice that here we don't have the immediate addressing, okay, we don't have this hash symbol. So this is then, we'll add the contents of address 52, which is 49. So I guess, what, 48 plus 49, that should just be 97. Right, then we have LDR2, and let's just see what that does. So, right, LDR2, that's using immediate addressing, load the number n, right, into the index register. Right, so what we're doing then, we're loading 2 into the index register. Right, let's just do that there. Right, then we're doing LDX50. And what this is going to mean, right, so it's using indexed addressing, form the address from the address plus the contents of the index register. Right, copy the contents of this calculated address to the accumulator. So, right here then, right, so we go to 50. But what we're actually doing is, well, we're doing 50, okay, plus the contents of the index register. So that means, right, 52. So what we have to do, we have to load the contents from 52, right? So I guess this 49 here. Right, so yeah, we load 49, right, then we just decrement the accumulator. So of course that's going to go to 48. Right, the last one, we load 52, we then, right, So again, well, load direct, right, then we subtract using direct addressing, so memory address 54, right, then just increment the accumulator. So 52, that's going to be, right, this 49, then, well, actually I forgot, right, then subtract 54, so right, well, 49, right, subtract 6, that's going to be 43, right, then increment the accumulator, that's going to be 44. Now I'll just demonstrate how we can actually write our own and test assembly programs using this site here, asmcode.pro. Now, of course, well, I'll just copy down the memory address contents here, and note that the question actually started at memory address 48, so let's just go ahead and do that, and you can see that's updated now. Right, I'm just loading 50 into the index register, also loading 2 into the accumulator. Yeah, that was just the starting conditions they told us. And then, for example, this here, this is program 3. Now we can go step cycle to see each stage of the fetch to code execute cycle, or for example we can go step instruction. So let's just do this. So we see, well, currently we're on this line, we've loaded 50 into the index register. Right now we've loaded 2 into the accumulator, we can see here. Right then we load 2 into the index register. Then we use index addressing. And what we're doing here is, well, we have here 50, right, plus the contents of the index register 2. So effectively here we're loading from address 52. Right, yeah, then we decrement the accumulator, and I guess here we just end. And of course here we can see 48, right, which is the answer we actually got on the paper. And of course you can also make a trace table. If you've seen the other videos, then you'll know this. Yeah, just automatically generate. Yeah, so I think for that should be okay. Right, then the processor includes these bit manipulation instructions, right, so and, XOR, or, right, logical shift left and logical shift right. Right, again, the contents of memory like this. Complete the table by writing the contents of the ASCII after each instruction is run. The binary number, okay, well, that's kind of, well, I mean, it depends if it's signed or unsigned. Of course, if it's signed, that's going to be, what, -1. If it's unsigned, it's going to be 255. But anyway, that's reloaded into the accumulator before each instruction is run. Right, so first thing we just want to do a logical shift left of 2. Yeah, okay, so I'm just going to do this one here. So if we're shifting left by 2, we can think, well, these 2 positions, right, they're going to get shifted out. So of course, well, yeah, these 6 are obviously going to get, shifted 2 positions to the left. And then what's going to happen is, well, two zeros are therefore going to come in from the right. So, I mean, that one's quite easy, right? It's just going to be, hang on. Okay, yeah, it's just going to be 6 ones, right, and then 2 zeros at the end. Right, then we want to XOR with 100. And, be careful with this, right? This is not the value this is not the denary 100, right? Of course, it's the memory address 100. So yeah, let me just erase this, and I'll just write this underneath. Right, so 100, okay, that's going to be, right, 4 zeros. Yeah, hopefully that's correct. Now, what we can say then, XOR, if the 2 inputs are the same, it's going to be 0. But if the 2 inputs are different, it's going to be 1. So here, well, 1 and 1 are the same, therefore it's a 0. Right, 1 and 0, they're different. Obviously, right, same, different, and then yeah, so all different like that. So yeah, that should be correct. Right, and then, I mean, something to note as well is that if we XOR something with all ones, well, that's just going to invert these. Well, it's going to invert the other input. So effectively, we can see that here, right? Because, well, this 0 has become a 1, this 0 has become a 1, this 0 has become a 1. And then obviously here, well, these ones, right, they've become zeros. So yeah, this one we can easily check, right? I mean, basically this it's just doing the same as a not. Right, then the next one we want to AND with 103. Right, okay. So actually, I mean, this one is also quite easy because, well, here they're all ones, right? Therefore, if we're ANDing with, well, with this, then whenever we see a 0, it's going to be a 0, and whenever we see a 1, it's going to be a 1. So effectively, like, this will just be our answer. So yeah, let's try and remember that. So what, 0, 0, 1, 1. Yeah, I think that was correct. Yeah, okay. And then of course, while this, yeah, this XOR 1, right, we would also, yeah, obviously want to, write here. Right, a theatre wants to use a database to store data about the shows that are scheduled, their customers, and the seats the customers have booked. Right, in the theatre, each show can take place on multiple dates. Some dates can have more than one performance. There are multiple rows of seats, and each seat can be individually booked by its row letter and seat number. Right, for example, E and seat 2. Right, part of the database design includes these three tables. So show has a show ID, title, duration. Right, seat ID, row letter, seat number. And then performance, which has performance ID, show ID. Show date and start time. Right, so here we want to identify the relationship between the tables performance and show. So when it says relationship, another word, I think they don't really use it often. Maybe I've seen this like once or twice. So they might say the cardinality, and the cardinality just means, is it one to one, many to one, one to many, or many to many. So let's think then of performance. Well, a performance has this show ID, which this suggests that, obviously each show can have many different performances. For example, let's imagine we have a show, I don't know, maybe like Lion King. So Lion King is obviously going to be the title. Now you might have obviously Lion King 3 times in one day, and that's going to be the different performance ID. So here then that's going to be many to one because we have many performances for one show. Right, sample data for the table performance. Write a structured query language SQL script to define the table performance. Right, okay, so when it says define, of course that just means create. Right, let's go create table. And probably they didn't say create because, that's going to be too obvious. Since that's also the name of the instruction here, or the keyword. Right, so create table, and then we say performance, and let's also capitalize it correctly. The same as they've done. I think that's spelled correctly. Right, then what we want to think, so performance ID. Right, this is going to be a varchar. Now, in the other paper, I did wonder, if they have an integer like this, of course, starting with leading zeros. Like, I think sometimes I've seen them say, this is an integer, but of course, in reality, like an integer can't really start with leading zeros. So I think that's why they're going to store it as a varchar. Right, so that's going to be performance. Okay, let's go performance ID. Right, let's just go varchar. Now, to be honest, like here we can say, of course, all of these are going to be 4. However, we might have a situation where, of course, if we have more than 9,999, then of course it's going to go into 5 digits. So, like, I don't know. Maybe if we just go varchar 4 is going to be okay. You could go something like varchar 10. Of course, inside the brackets. Now, I do notice actually in the mark schemes, they often don't actually include the size, because what the size is saying, that's saying the maximum size, right, of this varchar. So I think in real SQL, you have to specify the maximum size. Maybe there'll be a default value, but I think you have to specify it. Right, anyway, let's just go comma, and to be honest, I'll just put maybe like 10 in brackets. Right, then the next one's going to be show ID. And that's again just going to be a varchar. And I don't know, this one, let's say like 6, or it should be enough. Again, make sure to have the comma separating kind of each field. Right, then show date. That's just going to be date. Right, and then start time. And here SQL, they also have a time. I think they have time, they have date time. So date time is going to be both the date and the time. Of course, date is just going to be the date, time is just going to be the time. Right, then we want to think the primary key. So the primary key, and the way we do that as well, we just write primary key. And then the primary key that we're going to choose is going to be in brackets. So that's going to be performance ID. And this one we actually have to be careful. I think a lot of people wouldn't have probably done this, but we think this show ID, this is going to be a foreign key, right, to this show table. So what we then want to say, let's go foreign key. Right, that's a K. Right, so the foreign key, that's going to be this, right, show ID. And then we just want to use references. So yeah, let's close the bracket. Then we go references, that's another keyword. Then we want to say, well, the table and the field that is the foreign key for. So that's going to be what show. And then this one should go inside brackets, and it's going to be show ID. Yeah, that should be okay, and make sure let's to close the brackets there and then just have a semicolon at the end. Right, then we want to write an SQL script to return the number of times each show is scheduled. For example, in the sample data in part B, the show MK12 is scheduled 3 times. Right, the result needs to include the show name and a suitable field name for the number of times it is scheduled. Okay. Right, so when it says show name, well, that's going to be in the show table, or yeah, the show relation. Whereas the number of times it's scheduled, yeah, that's going to be in this performance. So effectively, we need to join them. And what we're going to be doing is, well, we're going to be grouping by this show ID, right? And then we just want to count. So yeah, I mean, basically, well, we want to count, you know, obviously how many are in each group. And like if people are kind of struggling with SQL, I mean, well, I have one example on my site. This is another website I've recommended a couple of times. I think it's sqlzoo.net, and here this is like the pseudocode or assembly website. You know, you can type in your SQL directly into the site, and yeah, it's just going to execute well on the server. Yeah, it's going to sort of, you know, say if you're correct or not. So that's a good way to practice. Now, if you actually want to download, let's say, well, MySQL onto your computer, one way you can do it is something called XAMPP. Right, another way where you go to the sort of Oracle website, download MySQL. There's also a program called, I think it's SQL Workbench, or yeah, MySQL Workbench. And yeah, that's also useful for kind of letting you run SQL scripts. Right, anyway, so what we want to do then, we want to go select. Right, and then so what we want to select, so we want the show name, so that's going to be what show. So we want to say the table. And then I think what is title. Right, then we also want to select the count. Alright, so yeah, that should really be capital letters, although I think it doesn't really matter in SQL. You know, it's just convention. Right, so count, and then, I mean, here let's count what's from the and okay, hang on, right, show should be capital letters, since yeah, the name of the relation is capitals. Right, so here this is then going to be performance. And you know, for here we can actually choose any of these fields. Let's go performance.showID. But yeah, I mean, if we choose any of them, right, it's going to give us the same result. Right, then we want to say from. Now here we can actually choose either table, so we could go from show, from performance. I'm probably going to go from performance. But again, you know, it doesn't really matter, you can choose either. Because whichever one, whichever one you choose, well, you just have to do inner join with the other one. And actually, I will actually just add something here. So let's go, because what it says, right, yeah, and a suitable field name for the number of times it's scheduled. Because otherwise, if we just have this, I mean, it will literally have the field name as being this. So the field name will literally be count performance, you know, .showID. So if we want to change that, well, then we can go as, and let's call maybe, I don't know, like scheduled amount or something. Alright, yeah, sorry. Right, so let's go as scheduled amount. So the whole thing is going to say, well, count performance.showID. Alright, then, yeah, as scheduled amount. That's going to go here after this one. Right, from performance, then we want to go inner join. And then here, well, we want to inner join it with show. And we then want to say on. So on, these are going to be the fields that are equal. And the fields that are equal, well, it's going to be the show.showID. Right, and then, yeah, so where that is equal to the performance.showID. Yeah, so I think, I mean, that's quite a difficult question, but I mean, hopefully that's correct for 4 marks. Right, customers give their first name, last name and email address when they are making a booking. One booking can include multiple seats. Describe the additional tables that will be need to be included in the database and explain how these tables will be linked within the database. Right, okay, so let's just go up here to see what we have already. So of course, well, one new table we're going to need is going to be customer. And we think, well, customer, for example, well, that can obviously include, well, like a customer ID. Let's just say CID, or I'll keep it short. Of course, what's going to have what the name, let's say, right, the email, yeah, maybe some other things. Yeah, it doesn't really matter. Right, I guess we're also going to need a booking. And then, of course, well, one thing the booking will need will be the customer ID. Right, another thing the booking will need, I guess, well, what performance they're going to see. So I'd say PID. Then finally, we're just going to need some way to link the booking with the seats they selected. So here, let's have another table. Let's call it maybe booking seat. And this is actually going to be a bit redundant because I guess, I mean, the primary key, again, it's just going to be a composite key of these. So that's going to be the customer ID, right? Also, yeah, okay, all right, let's go also the performance ID. So effectively, you know, this is a kind of, well, composite key, right, for the booking. Yeah, it's going to be a foreign key for that table. Right, then we just want to go the seat ID. Now, in reality, like in this example, it seems, yeah, kind of a little bit redundant because, well, we've got this here, we've also got this there, and you know, here we're not actually storing any extra information. But I guess if this was a real database, I mean, you might want to store extra information with this booking. For example, like whether it's successful, you know, maybe the date they booked, yeah, maybe, I don't know, like, you know, various other information you might possibly want to store. And I mean, I did just check the mark scheme, and yeah, this is what they've also done. Right, so then we just want to explain how this works. So let's say what a customer table. Yeah, right, so a customer table should be created. Right, yeah, which will store a customer ID. Yeah, let's say customer ID, right, name and email. Right, let's say a booking table will be created. Yeah, I mean, all right, let's not say will be created, it's going to take up too much space. Right, let's say booking table. And let's say, I mean, right, what's that going to use then? So we said that's going to use the customer ID and the performance ID as a composite key. Right, okay, yeah, let's say we'll use, okay, use, right, customer ID and performance ID. Right, yeah, let's say as, well, maybe as composite primary key. Right, and then we can also say the customer ID will be a foreign key to the customer table, and performance ID will be a foreign key to the performance table. Right, yeah, the customer ID right, will be a, well, foreign key to the, well, customer table. Right, yeah, and the yeah, well, and the performance ID. Right, yeah, will be a foreign key. Right, to the performance table. Right, I'm not going to write the whole thing. Right, then let's also say booking seat. And then this one, what this is going to use the, well, it's going to be a composite key of the customer ID, the performance ID, and seat. Right, so yeah, let's say composite, right, let's say PK primary key, right, of, well, CID, customer ID, performance ID, yeah, and well, SID, right, CID. And again, let's say, well, right, customer ID, right, that's going to be a foreign key to the customer table. Performance ID, well, foreign key to the performance table. And then obviously, well, seat, that's just going to represent their seat. So yeah, I mean, I think hopefully that should be enough for 5. Right, the next one, a multimedia design company has an office with a LAN, local area network. The LAN can have up to 20 devices connected with cables and other devices connected using wireless access. The company has private cloud storage for its employees to store their work. Define the term private cloud. So if we break this down, then, well, private means, of course, it's only for that company, and, well, cloud, that just means a sort of remote location, right, remote server. So let's just say, I don't know, maybe storing the data, or yeah, storing the work. Right, let's say, yeah, on a remote server. Right, yeah, that is only available for this company. Or I guess, yeah, we can say maybe only used for the, you know, by this company. Yeah, so I guess, I mean, well, they could just have sort of one server, you know, they could have a whole data center, yeah, just for them. Right, describe the benefits of the to the company of using private cloud storage instead of public cloud storage. Right, so I think this one, I mean, well, the obvious one is going to be security, privacy, because they've got their own, yeah, their own kind of, well, servers. Another one, maybe you say sort of customizability, because if they have their own servers, of course, well, probably they can customize them more. You know, they can sort of buy specific hardware. And then I guess a third one, I mean, you could possibly mention, for example, not only can the hardware be more specialized, but even the use case can be more specialized, like what they're actually running. Because let's say some public cloud, like they might have restrictions about what you can run. If you want to run some, you know, high intensity GPU stuff, or, you know, something like some cryptocurrency miner, you know, that's probably against their terms of service. Whereas if they have a public cloud, I mean, basically they can do whatever they want. Yeah, kind of assuming it's still, you know, within the laws of that country. So let's just say, well, security and privacy. Yeah, I mean, you could probably explain that more. You could say, well, security and privacy maybe will be higher. Right, yeah, since these servers are only used for this particular company. Yeah, right, only used by this particular company, right, they're not shared. Right, let's say also. Right, so I think the second one, maybe we can say the hardware can be more customizable. Yeah, let's say, right, the hardware, right, can be more customized. Right, for their particular tasks, or yeah, for their particular use case. And I don't know, we can give an example, right, e.g., right, they require lots of GPUs, right, or maybe they require lots of bandwidth. So yeah, I mean, lots of GPUs you can say for example, AI, right, something like that. Right, let's just say finally. So finally, right, since they own the, or well, yeah, since they're, I guess, the owner of the cloud. Right, since they own the cloud, then they have more freedom about what can be run. Yeah, let's say more freedom about the processes they're running, right, on those devices. Right, yeah, about the processes. So of course processes just means, you know, programs, well, running programs. Yeah, that they are running on those servers. Yeah, alright, so I think that should be okay. Part of the internal structure of the wired LAN is a star topology. Explain how packets are transmitted between two devices in a star topology. Right, I mean, so let's just try and draw this. So a star topology where you have a central switch. I mean, it could be a hub, but yeah, usually a switch. Right, then of course, where you're just going to have the individual nodes coming off of that. And the difference between a switch and a hub, well, a hub can only do broadcast. So that means, let's say, this device sends to the switch. Well, then, that data is just going to be broadcast to every single device. Whereas a switch, that can do unicast, multicast, and broadcast. So remember that unicast means, well, sending just to one device. Multicast means sending to multiple devices, let's say maybe this one and this one. And of course broadcast, well, that means sending right to all the devices. So right, let's just say that maybe, yeah, I know 4 nodes to communicate. Right, let's say, yeah, I know packets are sent to a central switch. Right, and let's say, yeah, which can forward those packets onto the correct receiving device. Yeah, forward those packets. And this, like, I mean, usually this would be by MAC address. Right, yeah, forward those packets onto the correct receiving device. Now, some switches, they can forward packets both by MAC and IP, but really this just depends if it's, okay, something called a layer 2 switch. So a layer 2 switch, well, this works, I guess what you call that, the data link layer, right, also, well, kind of informally thought as the kind of Ethernet layer. Right, since Ethernet is the main protocol. Whereas if we think layer 3, now layer 3, that's going to be the network layer, okay, so using TCP IP. Yes, there's actually 2 types of switch, but the main one is apparently like an Ethernet switch, right, a layer 2 switch. So yeah, that's going to use a MAC address. Right, so onto the receiving device, yeah, based on their MAC address. And again, I think, we can also mention, because, well, hopefully that's 2 marks, but we could mention, yeah, I know star topology supports, right, unicast, multicast, and broadcast. And I mean, it's not really a star topology, I suppose it's really a switch. Alright, so let's say switch, yeah, obviously supports, well, unicast, multicast, and broadcast. Now, obviously, again, if it's a hub, right, then it's only going to be broadcast. Right, a different part of the network uses the Ethernet protocol. A collision is detected. Describe how the collision is managed using carrier sense multiple access with collision detection, or yeah, CSMA CD. I mean, so collision, again, hopefully people remember this, but I mean, all right, maybe let's not draw it like this. Right, so let's say this is our bus line, and of course here we just got different devices coming off the bus line, maybe just like 3 devices like that. Now, let's actually use a different color, maybe this, yeah, orange. Right, let's say if this device here, A, and maybe this device, let's call it B, right, if they're both sending at the same time, so let's say, right, A is obviously sending data, right, it's going to be, yeah, going along the wire, and let's say B is also sending data at the same time, well, of course, then you're going to get the collision, right, that's the interference. So what's going to happen? Well, these devices, they're going to detect there's been an interference, detect there's been a collision. And I guess, I mean, here it's saying what a collision has already been detected. So we then want to think what happens, and well, here it's going to be a jamming signal. Right, so they send out, yeah, a jamming signal, and that's going to be to let all the devices know a collision has occurred. Yeah, or let's say all the nodes or other devices. Right, no, a collision has occurred. Right, let's say, well, devices will then stop sending. Right, then they'll wait a random amount of time. Right, yeah, wait random amount of time before resending. Yeah, and I guess we can say, like if no collision is detected, you know, then it's successful. Yeah, probably that's okay. Right, yeah, if no collision detected, let's call this maybe retransmission. Right, retransmission, yeah, has been successful. Right, and then I guess what we can say is that yeah, I don't know, like maybe I'll just do it here, you know, you could sort of write it at the end. So let's say, well, random time, let's call it RT, right, is used, let's say to prevent kind of like repeated collisions, because otherwise if they both wait, let's say, you know, 0.1 seconds, well, then there's going to be another collision. Yeah, let's to prevent, let's call it repeated collisions. Right, then we want to identify two drawbacks of using CSMA CD. Okay. So I think, you know, the problem with, well, I mean, the problem with the bus network generally is that it's not really that scalable. You know, you can't have many devices, because let's say if you have like, I don't know, 20 different devices, well, realistically, like more than one of them is going to be sending data at the same time. Like if you think, I don't know, let's say you're like watching YouTube or, you know, some live stream, like you're always going to be sort of, well, downloading or uploading data, and like in that case that means that no one else can use the network. So yeah, maybe let's say that. So I guess we can say, well, for networks with large number of nodes, right, for networks yeah, with lots of nodes, right, let's say, yeah, there will be a large number of collisions. Right, yeah, large num of collisions. Right, hence network will become slow. Right, and then I think another one, you can probably mention that sometimes the random time kind of fails. Like if they both generate the same or kind of a similar random time, then, you know, you can get another collision. Of course, I mean, if it's slightly different, it should be okay, because I mean, well, the devices will read the voltage on the line, and if it detects that, you know, the voltage is not zero, so of course, right, if we have, yeah, some voltage, well, then it just won't send, right? It will just continue waiting, because in this case it knows that someone else is sending. But let's say, well, let's say, yeah, it's possible, right? It's possible. Yeah, so I guess, well, it could be like many devices, right? Many devices wait the same amount of random time. And then I guess we say, well, and get repeated collisions, right? Yeah, and hence cause repeated collisions, or maybe result in repeated collisions. Let's just call that RC. And yeah, obviously in the exam, you know, write repeated collisions. Right, the devices in the office have static private IP addresses. State what is meant by a static private IP. Right, so obviously here again there's going to be two parts, static and private. So let's say static, well, this means the IP address won't change. Yeah, let's just say that. Right, the IP address won't change. Yeah, I mean, I think, well, won't change or won't change when the device is switched off. Yeah, I think just won't change. You know, of course, well, unless the user kind of manually changes it. I mean, yeah, maybe let's write that, right? So unless, or let's say the network admin or yeah, the user, right, manually changes it. Right, and then let's say private. So private, well, that means the IP is only visible within that network. Right, yeah, let's say private IPs, right, are only visible. Yeah, let's say, well, within that network, right, or within that LAN. Because, well, in this case, they're talking about a LAN. But yeah, I think that should be okay. And actually, I mean, this one is kind of weird because, like, they kind of got 2 points, but yeah, right, you've only got 1 mark. Question 6 says each of the following truth tables has 3 inputs A, B and C and 1 output X. We want to draw one line to match each truth table with its logic expression. Right, so this one is a bit tricky because, I mean, we can't just use the sum of products because, I mean, none of these are in the kind of sum of products form. And, you know, the sum of products form, that's going to be something simple, like we're just going to have, yeah, say, I don't know, maybe A and not B, right, and C. Yeah, then or, I don't know, maybe not A, not B, and not C. But, you know, here we've got XORs, we've got NANDs, right, so it's not going to be correct. I mean, the way you would do it, though, with sum of products, let's look at this one because it only has 2 cases where they're true. What you do is, well, you look for the true rows, right, so these two, and then if we see a 0 input, then we say not, right, if we see a 1, well, it's just, you know, the regular, well, in this case, C. So here, the way we'd write that is going to be, well, not A, right, and not B, right, then and C. And if you're not familiar with this notation, well, yeah, this, I'm not going to do 2. But okay, let's say this line, right, that just means not. Of course, yeah, this circle or this dot, that just means and. Right, then you just OR it, because what we're saying is well, X is true, right, if either, you know, this row, right, this condition is kind of valid, yeah, or, you know, if we're in this condition, or, yeah, this situation. So this last one, which is going to be what A and B and C. But again, right, none of the answers are in this format. So yeah, I guess we can't really use that. So I think what I want to look at, I just want to look through some of these and see if there's any that we can kind of easily discount. So I think, yeah, maybe this one we can have a look at. Because, you know, or C, well, if we have or C, then we know automatically that, you know, 4 of these are going to be 1. Right, so I'm just going to write it for this middle one. Now, where C is 1, then of course that means the output should be 1. So here we should have an output of 1, right, here we should have an output of 1, right, again 1 and 1. Right, then we want to say A, NAND, B. So if we think and, well, and is going to be true, right, only on the last condition. So yeah, when both inputs are 1, right, then and will be true. Therefore, well, NAND is just the opposite. So NAND is going to be false when both inputs are true. And obviously, yeah, true in all the other situations. So let's say then, right, if A, so like in this case, right, so A NAND, well, yeah, 0 NAND 0 will be 1. Again, right, 0 NAND 1, that's 1, that's 1. Right, this one will be 0. So is there any that matches this? And yeah, so I guess this this bottom truth table here, right, that's going to be this one. I think, I mean, maybe let's have a look at this one, so right, A and B and C. Because here, well, there's only going to be one situation where this is true. And that's going to be, well, 1, 1, 1, right, so 1 and 1 and 1. But then when we not that, well, notting that, right, then it's going to become 0. But then if we think, well, every other situation, right, this and part is going to be 0, right, therefore when we not it, it's going to be 1. So effectively what we're looking for is we're looking for 7 1s, right, and then a 0. And yeah, so I mean, here they don't have that. So I think this one we can probably discount. Right then, I mean, yeah, I don't know, like maybe like this one we can probably try, because if we have an and C, well, and C means that, I mean, I guess here, well, we can write where it's definitely false. So if we have and C, well, this one has to be false, this one has to be false, right, this one has to be false, and this one has to be false. So if we look here, well, of course, yeah, this, right, I mean, it can't be that one, that's wrong. I mean, can it be this one? Yeah, so I mean, it's possible it can be that one. So I guess, I mean, now let's just try this then. We want to do the A XOR B. So what XOR is going to be when they're, yeah, okay, when they're different, it's going to be 1. Right? When they're the same, it's 0. So right, okay, yeah, well, they're the same, right? So it's 0. Here they're going to be different, so it's 1. Right, different, yeah, different. Right, then same, like this. Right, then what we want to do, well, we want to, you know, not this column. Yeah, all right. So let's not that. Let's go 1 1. Right, then we want to AND it with this C. So it's going to be what, this column, right, ANDed with this one. And I guess if we do that, well, we see, Yeah, so actually wait, there's none of them. Okay, alright, hang on. So wait, yeah, sorry, this one is going to be 1, right, that one's going to be 1. Yeah, okay, right, that one's going to be 1, that one's going to be 1. So right here then, so we expect a 1 in this row. We also expect a 1 here. Right, so does that match any of them? Yeah, so I think it's that second one. Yeah, okay, so this one we can see matches this second one. Okay, I've just erased that just so we can yeah, try and evaluate this one here, right, this A or C and not B. So I mean here you could just sort of instantly look at the not B. So not B, well that's going to be 1, so yeah, 1 1, right, 0 0 1 1 0 0. And then here, well, because it's AND, then it means that, well, the output can only be true, yeah, if this one is also true. So yeah, I think this actually matches, right, so far. Right, then let's do the A or C. Right, so I guess A or C, well, that's going to be 1 here, right, and then, yeah, then there's going to be a 1 here, right, there's going to be a 1 here, and I guess, yeah, then we've got 4 A's. Yeah, okay. Right, and well, then we just want to add them together. So, well, here we have, right, a 1 and a 1, so yeah, that seems correct. Right here we have a 1 and a 1, yeah, here we have a 1 and a 1. Alright, so I think that's correct. Now, if you had time in the exam, and of course, well, let's remember to link that. You know, if you had time in the exam, I would say probably check this one as well. Yeah, just to make sure, you know, that I guess we've not made a mistake. But yeah, I think for me, like, hopefully that's correct. Right, yeah, robots are used to serve food and drink to customers at a restaurant. A robot navigates through the restaurant to the table it's serving. Complete the table by identifying 2 sensors that can be included in the robot and the purpose of each sensor in the navigation system. Right, so in terms of, let's say, I mean, you want to obviously detect, like, when there's a table, when there's a person. And I think, I mean, sometimes they call it proximity. You know, so I guess we can also just call it infrared. Because a proximity sensor is just using infrared. Let's say, I don't know, to detect the presence or distance. Right, yeah, detect presence / distance of objects. Right, yeah, e.g. like tables, people. Right, and then, I mean, the next one, like, honestly, I wasn't really sure about this, but they actually give two answers. Yeah, they give 2 answers. One, they say sound, and I mean, really, that's just like a microphone. Another one they say is pressure, because they're saying, well, when people are, you know, putting food onto this tray, I guess, well, of course, you know, the robot will know, right, based on the pressure of that weight. And I guess, yeah, I don't know, when it has too much food, of course, then it's going to go back and, yeah, like, give that food, you know, so it's the kind of cleaning place. So, yeah, let's probably say that one. And let's say, well, this is to detect, let's say, when plates are placed on its tray. And yeah, let's say so it can return to the sort of kitchen. Alright, yeah, return right to kitchen. Right, the robot uses artificial intelligence AI to communicate with customers. The customers speak to the robot to order their food and drinks. Explain how AI will be used in this part of the robot. Right, so we can say, well, speech or, yeah, kind of audio, let's say speech recognition. Right, so speech recognition will be used to detect the words. Maybe let's say, yeah, to detect individual words. Right, that the customers say. Right, let's say, yeah, this is done by. And then I guess we can say, well, there's obviously going to be a speech recognition model which is trained, you know, using large amounts of, say, speech. And yeah, I guess probably that will be labeled data, where, for example, you'll have the word, and then you have, yeah, like the, well, okay, I mean, let's say you have the audio, and then you have like the subtitles for that audio. And then, yeah, I guess the sort of speech recognition model can then try to match the two, right, find the patterns in the data. So let's say, yeah, by training, or let's say by training a model, right, with large amounts of human audio, maybe, and subtitles. And then, I mean, yeah, for this we can call it labeled data. And the reason it's labeled is because, well, not only do we have just, you know, the input, right, the audio, but we also actually have the label. So the label is effectively saying, well, you know, what's the answer? Like, what is this? And if you think about image recognition, well, if we're using, yeah, labeled data for image recognition, let's say we have a picture, I don't know, maybe of like an apple or something. So here, well, of course, we have the picture of the apple, but then we also have text saying, you know, this picture is an apple. Yeah, just so the model can actually, you know, find links between the, I guess, between the features of the image, and yeah, obviously, like what the image actually is. Right, so speech recognition, yeah, to detect individual words that the customers, I guess, say. Right, this is done by training a model with human audio and subtitles. Yeah, okay, and then, I mean, that's fine, but if, like, there's a difference between kind of recognizing the words and actually understanding, like, what they're saying, in terms of, let's say, like, the semantic meaning, right, the grammar. So that can be done, I guess you say, what, natural language processing? Maybe, yeah, a natural language processing model. I mean, I guess nowadays, you know, you can also call this like an LLM, right, large language model. Yeah, that's kind of a more modern term, maybe. But all right, let's say, yeah, a natural language, right, let's say processing model, right, can also be trained. Yeah, and again, you could mention, you know, I don't know, like using like examples of human text. Right, let's say, yeah, in order, right, so in order for the robot, right, to understand what the words mean. Right, yeah, let's say, like, e.g., right, the order, yeah, I guess what the order the customer is placing. And this natural language processing is not really as easy as some people might expect. You know, people might think, well, the robot can just listen for keywords like burger, you know, Coke. But of course, you know, let's say if someone says something like, maybe I'll have a burger if you don't have any pizza. It's like, well, of course, you know, they're actually asking for pizza. And obviously, yeah, they only want burger, like, if they don't have a pizza. So yeah, there's obviously the kind of grammatical meaning or the semantic meaning it also has to understand. Right, anyway, the navigation system can be considered an example of a control system. Describe how feedback is used in a control system. Right, so if we think of an example like a temperature example, let's say we have I don't know, like an ideal temperature that's between, say, 25 and, I don't know, maybe 21 degrees. Now, if the temperature goes above this, well, then, like, I don't know, let's say they turn on the fan. And then what's going to happen, of course, well, hopefully the temperature is going to decrease. And then, of course, well, that temperature is going to be measured again, right? So this is the feedback. And if the temperature is now within the normal range, well, then, of course, the feedback is saying, right, you should now turn off the fan. Whereas, of course, you know, if the temperature is still too high, well, the feedback now is saying, you know, continue using the fan. And, like, if for some reason the temperature has got even higher, well, yeah, then there must be something kind of drastically wrong. So this is what we just want to say. And I think the way they really say it is they say, well, the output of the previous result can then be used, let's say, to, well, change the system, right, or to affect the input of, you know, the next stage. So let's say, yeah, the previous output, right, or the previous sensor output, right, let's say can be used, yeah, to modify, and then let's say to modify like the system. Let's say, right, and hopefully bring, yeah, let's say hopefully bring the next inputs, or yeah, well, I guess we can say the sensor readings, right, next, or let's say, yes, sensor readings, and then we'll probably put input in brackets. Yeah, right, input, let's say within the normal range. Yeah, and I mean, I think that should be enough for 2 marks, I hope. Right, the robot includes a touchscreen for the customer to make the payment. Describe the principal operation of a touchscreen. So this one I do actually have a picture, and of course touchscreen, there's 2 examples. One is going to be a resistive touchscreen, where I guess, well, here we have, you know, right, a top electrode, a bottom electrode. You can say, well, both of them are going to have an electric charge flowing through them, and you know, when someone touches it, like, I mean, this top electrode is actually soft. Now, if people know an example for something like a Nintendo DS, right, this is going to be a resistive touchscreen, because if you touch it, right, that's actually, I mean, basically it's a soft screen. Some ATMs, right, yes, some ATMs are also resistive, although we'll see some ATMs are also capacitive. But anyway, so yeah, when you touch it, well, now basically here where they touch, of course that's going to like cause a change in the current, or, well, I mean, you can say it's going to cause a circuit to become complete, and of course, yeah, where that circuit is complete, well, yeah, here is where it can obviously detect, right, this is where, yeah, this is where they touched, right, because that's where the circuit is complete. Right, then the next one, well, capacitive, what you're going to have here, we say, well, this layer is going to be electrically charged. So I think probably it's going to be negatively charged. Yeah, it doesn't really matter. And then what happens is, well, when the person touches it, you know, this charge is then going to be kind of absorbed into their finger. So we might have a situation where, let's say here we have a charge of like -1 volts. Here we have also -1, but you know, where they touch it, right, let's say that goes to 0 or to, you know, 0.5. And of course, wherever they touch the screen, well, yeah, that's where it's going to be detected. And I think you can say, for example, an advantage of capacitive, well, for example, you can like touch multiple positions, and it basically the touchscreen will be able to detect those multiple positions, whereas, yeah, resistive you can't. Also, capacitive supports things like gestures. So let's say on your phone, right, because a smartphone is going to use a capacitive, you know, this second example, you can do things like swipe, right? So if you swipe with multiple fingers, you know, of course, to like go forward and back, right, left and right. You can also like pinch fingers, let's say to zoom in, zoom out, yeah, all of those kind of gestures. Right, so let's just try and explain how that works then. And I think here you can describe either a resistive or capacitive, or yeah, maybe let's do both. Right, so touchscreens, right, can be resistive. And let's say, right, let's say a soft upper layer, right, or a soft film is used. Or, well, okay, let's say maybe a soft, yeah, I guess film, right, is used. Right, there's going to be what, 2 layers. Right, and yeah, I guess what, and when the layers touch or when the layers connect. Right, let's say when the layers connect, then an electric charge is induced in that area. Or yeah, let's say maybe let's say the circuit is complete in that area. Yeah, let's say right in that position, I guess. Right, then let's say for capacitive. So what we'll have is we'll have an electrically charged layer. Right, and let's say, yeah, and where the user, and alright, let's say maybe the charge is absorbed. Yeah, or I guess maybe removed, right, the charge is removed. Yeah, where the user touches. Right, and then I think we can say, let's say in both in both situations. Right, let's say these coordinates. Yeah, okay. Or we can say, well, the touchscreen will convert, these electrical signals into coordinates. Yeah, I mean, you can say maybe the driver or the firmware. Let's say the touchscreen. Right, the touchscreens. Yeah, let's say firmware. Right, will convert. Yeah, let's say, well, this location into coordinates. Right, and then we can probably say, yeah, and send it onto the microprocessor. Yeah, or maybe, well, and send these coordinates onto the microprocessor. Let's just go on. Yeah, I guess, and if we want to expand that, well, to the microprocessor for it to determine. So, well, for it to determine, let's say, what action to perform. Right, e.g., like, yeah, maybe which button was pressed, like where they, yeah, I don't know, like what they clicked on, right, something like that. Right, and then is this, yeah, I think the last one. So let's try quickly. Right, program libraries were used when writing the robot software. State what is meant by a program library. So here we can say, well, code. I can also say, functions, procedures, modules. Right, let's say written, let's say previously. Right, by, let's say maybe other, well, programmer or programmers. Right, let's say, yeah, that can be imported into our project. Right, so yeah, the next one, some program libraries include dynamic link libraries or DLL files. Describe the benefits of a program using a library with DLL files instead of using a library that does not include DLL files. Right, I mean, so what this is saying then is, well, when you compile something, so let's say this is our compiled executable. Now you could have it where, you kind of bundle, let's say, well, static, right? So static libraries, as part of this, as part of this executable. But I guess the problem with that is, well, I mean, the executable is going to be pretty big. Also, another problem is, let's say someone has that executable. Now, if you want to update the libraries, well, you have to send them an entirely new executable. For example, if there's a bug, a bug fix or something like that. Whereas if we're using dynamic libraries, well, here let's say we have well, DLL1, right, DLL2, let's say what DLL3. Here you just have a link to that, and for example, it will say, I don't know, like import. Like maybe there's a library like let's say Windows, right, system32.dll, for example, some like Windows DLL or something. So when you then open this executable, well, then Windows will look, right, to try and find a DLL with this name. And of course, if it finds it, well, then it can actually load it and kind of execute it, run it. Of course, the problem is, like, if the DLL doesn't exist, well, then the program is just not going to work. So I think for the first one, let's say that if the maybe if there's an error in a library, so let's say that, or yeah, maybe if a library needs to be updated. And I mean, let's give reasons for why it has to be updated. Let's say maybe new features. Right, let's say fixing, so like bug fixes. Yeah, I mean, so if you think, well, obviously we've got adaptive, perfective, and then, yeah, well, corrective maintenance. So let's say, I don't know, fixing bugs, right, / security vulnerabilities. Right, so if a library needs to be updated, I guess, well, let's say we don't have to recompile the executable. And I mean, well, the reason for that, unless you say what, since the new library will be automatically imported. Right, I mean, I think you could mention that, for example, sometimes you can kind of defer loading of these. So let's say like most of your program, doesn't need a particular DLL, right? You can have it where it's only going to look for and load that DLL, when it's required. And I guess in that case, you'd say, well, the startup time of the executable can be faster. Yeah, although maybe, I don't know, can we think of a more simple example? All right, no, I think let's go with that. So we'll say maybe, all right, let's say program startup can be faster. Yeah, all right, let's say program startup can be faster. Right, and also memory usage can be lower. Because what we'll say is, well, the DLLs can be loaded. Let's say, let's say loaded into RAM and removed from RAM. Yeah, when required and not required. Right, so yeah, loaded / removed, right, from RAM. Right, let's say, yeah, when required. Yeah, I guess, right, or not required. Yeah, so I think that should be all right. Then, yeah, the last question, or well, two more. Right, the data from the robots is transmitted to a central computer using wireless connection. Complete the table by identifying and describing two methods of data verification that can be used during data transfer. Right, so one, I guess, well, let's say parity check. Yeah, or parity byte, parity block. And then for here, let's say counting the number of ones. Right, counting the number of ones in the data. And let's put in brackets, right? Let's say, yeah, which would have been split into, right? Okay, which would have been split. And I think the other question, they said into 7 bits. So let's just go with what they say, right? Into 7 bits. Yeah, I mean, well, I guess yes, into 7 bits. Okay, right, so counting the number of ones in the data, which would have been split into 7 bits. Right, let's say, yeah, and using either odd or parity, right, using right, either odd or even parity. Right, let's say, yeah, the parity bit will be added. Yeah, or let's say to make total count of ones, right, odd or even. Yeah, all right, let's say, right, odd, yeah, or even. And then let's say, I know parity is kind of like checked by receiver. Or yeah, let's say, right, parity recalculated by receiver. Or I guess we can say, well, recalculated / verified by receiver. Let's say verified, right, that's just one word. Right, and then I think another one, I mean, let's just go with checksum. And if people want to actually look at this, I mean, you can download a program called Wireshark. And if you actually look in Wireshark, this will show you the traffic, right, being sent, into your computer and out of your computer, right, incoming and outgoing. And then, for example, yeah, you can actually see the checksums that's being calculated. And I think that's going to be part of the network layer. Okay, so the IP, the IP layer would add a checksum. So what this is going to be, let's say, maybe perform a calculation on the data. Yeah, well, let's say, yeah, I mean, yeah, let's say, right, on the data. Right, let's say to generate a checksum. All right, let's say a sequence of bytes, right, or bits. Because, well, really, the sequence of bytes is the checksum. Right, perform a calculation on the data to generate a sequence of bytes. Right, let's say and maybe add this to the packet. So I think that'll be what added to the packet header. Right, add this to the packet header. Right, let's say, receiver. So maybe we want to say they would use the same checksum algorithm. Because of course, if one of them is using, say, MD5 and one is using, let's say, like SHA-1. Okay, no, not SHA-1. Let's say what SHA-256. Secure hashing algorithm 256. If they're using different algorithms, right, they're going to get different results. Right, so receiver uses same hashing algorithm. To ensure they calculate the same value. Or maybe calculate same checksum. Right, let's say if not, then error has occurred. Right, then we want to explain how encryption can protect the security of data during transmission. Right, so I think for this one, they often mention encryption algorithm and key are used. Right, encryption algorithm, right, and key are used. And then we want to say, to convert what to what, right? So to convert, that's going to be plain text, right, into ciphertext. Right, let's say if an eavesdropper. So an eavesdropper, this is someone like kind of listening into the network, right? So you can say a hacker. Let's say, if an eavesdropper intercepts this data. Right, let's say they will be this data. They will be they will be unable to understand it. Right, unable to understand it without the decryption key. Alright, so again, guys, that was a super long video, but as always, hope it's useful. Any questions, ask in the comments, and if it is useful, see you again in the next video.